Hello, everyone. My name is Qingqing Mao, and today it's my pleasure to be invited to talk about building complex data analytics pipelines with Ray at this Ray Summit conference. And just to start with, just a little bit about myself. I myself actually has a PhD in astronomy and astrophysics, so I have some research background. And after that, I joined two startups back and forth. And before I was working as a senior staff data scientist at Primary AI, and at which we worked a lot on natural language processing data pipelines. And then now just recently, I changed to Dascena and to lead the engineering and the data science team effort here. And we mostly focused on applying machine learning techniques to healthcare and to improve the healthcare outcome. And I talked about this also because you can see like I have more a background in the mixed research and application experience. That's why a lot of things I'm going to talk about today is about how we can do research and prototyping and experiments with Ray. And a little bit outline about the things we're going to talk about. Basically, I'm going to talk about what's the challenge of a complex analytics pipeline here. I'll give some like examples in the NLP application and the healthcare machine learning. And also want to mention that there's a gap between the data science and engineering. I think a lot of people have been talking about this, and I'll give more examples on that. And then how Ray can actually help us narrow the gap here we mentioned. Little bit about the examples in the talk. So the talk is more about how we can do faster development and iterations. For example, develop algorithm, running experiments, and doing prototyping. And how can we make the whole process flexible and portable that can later be deployed to different places. But this talk itself is less about how we do really large scale machine learning training. And we're not going to train GPT here, for example. And I'm not going to talk about like a low latency, large scale, real production deployment here. So it's more focused on experimenting and prototyping. So let me start with a very ideal setup. I think this is when we talk about modern day data engineers and data scientists and how we get things into production. And this is the very high level things in many people's mind. So you have some data engineers and their role is mainly get the data and how do you actually store and transfer and load data. And then prepare data, also including a lot of cleaning and these pre-processing steps. And then you have the data ready. And the data scientists now can work on the data and they will do exploratory analysis. And then most of the part is like model training and validating the result and testing the result. And there can be multiple iterations on there. And at the end, you actually deliver a model. So then the model will go to production, and then it feels like now it's the software engineer's job to actually deploy the model and worry about how we can run this in the runtime environment, how we can scale that to a really large scale. If we need, for example, some of the classifiers that needs to be run on like hundreds of millions of documents or images every day. This works actually fine overall for a well-defined problem. Like I say, if it's a classifier that, if it's like a image classification problem that you have a very well-defined problem set that you can have the model and then deploy the model, and that's fine. But my concern and my experience during my prototyping and experimenting in the industry is always, can we actually allow data scientists to even have more ownership along the pipeline? So can data scientists actually do more? I'll explain why and why do we need this. So in practice, a lot of problems I have seen is the task can be not really have a clear boundary and fix the input and output. So the task can be vague. So data scientists needs to actually touch more on the data pipeline side to get a good, and play with different inputs and different like data cleaning to actually get a better idea how they can do better job. So, and also a lot of times in your real system, it's not just a final machine learning model you deliver. And it's often common to have a combination of rule-based models, machine learning models, and also even some like external dependencies. And you need to combine all these things together. And in this way that you can have subtle dependencies between these. So your model will actually depend on some of your data pre-processing, and that pre-processing step may actually need to be propagated all the way to production. And also, like I say, I'm going to focus more on the research and the prototyping. So fast model delivery is less a concern I have here. Because a lot of times we don't need to actually, especially like in some of the research settings, you don't really need to, like for example, update the model like every day or like every hourly. So that we don't really have these needs. It's more about how you get a final solid model at the end. So I'll start with an example of a simple natural language processing pipeline. This is a little bit related to my work at Primary AI. And one of the general problems for natural language processing is, for example, entity extraction. And can you extract all these people, numbers, and locations, and all these different kinds of entities out of text, right? So a naive setting will be, you can feed in the text corpus, and there will be some like pre-processing, cleaning, and for example, segmentation and stemming, and some of like standard procedures on the text, and then you have that entity extraction model, and it applies on your clean text, and it gives you the result of the entities. So, and then you can just save that result, and the result can be ready to use for the application. So this actually fits the traditional pattern I was talking about, right? So if the data scientists only work on the entity extraction model, that's okay. So they can really just focus on how to get the entity extraction model the best performance. And as long as they train the model and deliver the model, and then if software engineers can worry about how we can scale that entity extraction part. But in reality, the little complexity will make the whole pipeline a lot more interesting and powerful. So what if we feel like it's not good enough to just do the entity extraction, and for a given corpus, we can also do some corpus level tasks, like for example, building a relation graph between all the documents, and also doing some other type of clustering and document assignment. And then we also have the entity extraction, and then we can combine these two results, and in the downstream task, we can have some entity linking. And there can be also external dependencies that link these entities to Wikipedia and all these like other external resources. So, but by adding that, it suddenly adding some dependencies between these tasks, because the data scientist can not only just focus on that single entity extraction block, because the entity extraction result may actually need to be combined together with external result and these corpus level tasks to deliver the best downstream result. And a lot of times it requires the data scientists to be involved end to end. And they need to be able to run the experiments from the processing all the way to the downstream tasks and see the final result and evaluate the final result, and tune all these subtasks as needed. So how Ray can help here? Right, this suddenly becomes a little bit more complicated here. And the problem is a lot of data scientists, let's just be honest, writing a really good parallel computing code is still generally hard for a lot of data scientists. So if the data scientist has more computer science background or like engineering background, so they're relatively okay. So they understand about scaling, they understand about these computing principles, and they can do better jobs with different like engineering tools. But that doesn't really apply for a lot of data scientists who are from a more science background. For example, bio, chemistry, physics, and math. And they are actually, a lot of people I have seen here, they are actually very comfortable in the Python ecosystem. They know how to do these analysis. They have advanced statistical knowledges, but the problem is they have less knowledge in distributed computing. And people can write some naive parallelization code, but when it comes to complicated these parallelized data pipelines, they're relatively powerless to do that. And if you can, yes, you can. Of course, you can actually mention there are a lot of tools out there, but each tool will have some learning curve for data scientists, and it will definitely take time and effort for them to fully understand and use these tools efficiently. And so there's a gap between these experiments and the production that actually slows down the development there. And data scientists also always they try to ignore some of these complex tools if they don't understand, and they just want to stick with their own workflow. But later, how do you port these things to production can be another challenge. All right. So what we can do is, if we actually look at that pipeline, right? So even there's these dependencies in it, and the interesting part is different blocks can be actually parallelized in its own way, right? So actually, if you think about more traditional in this distributed computing, this is actually, you can actually define a DAG and actually run the DAG that way. But like I say, so even these more complicated things, that can, a lot of times when you use some of the packages to define a DAG and define your run pipeline, you may need to significantly change your code structure, and that can be confusing. But on the other hand, if we use Ray, and we can just easily put some of the pre-processing function and as a Ray remote function, and then we can also have these document level tasks like entity extraction also as the same parallelized on document level. But for these corpus level tasks, they can be parallelized in actually a completely different level. So that will be, for example, some of the matrix operations that you can actually parallelize in a different way. And after you combine these two, these downstream tasks can also be parallelized in another way. So for example, you can have all the document level result, and you can have some clustering, and then you can do some of the entity linking on every cluster of the documents within your corpus. So, but for Ray, the easy part is you don't really need to introduce a lot of external tools, and you can simply have your you can simply still have your function in the old way, and by doing that, and all these Python code can still be reused and delivered later to other places if it's needed. And then, but you can have a pipeline just run the whole thing in the Ray.remote fashion. And then you can significantly reduce the time that people can run the end-to-end experiments. And the data scientists can actually run a larger scale tests by themselves. And as I mentioned, if you just ask data scientists to simply try Ray, and it actually enables a faster iteration, and it also allows a larger scope testing during development. And that can be really helpful. In the early days at Primary AI, and we really have kind of like a 2.5 data scientists and data kind of like a full stack data scientists and data engineers just using Ray. That actually helps us to reduce the pipeline running time like more than half, just with a few days of work, really. So that can be actually really beneficial, especially when you're in this startup and faster iteration kind of fashion. So I'll give another example that's more related to my current work at healthcare machine learning research. This is actually a workflow that's not only applied to healthcare, but also it's kind of like a general researching pipeline. I think a lot of people, if you actually do grad school research or academia research, you're also more familiar with that. So you have some raw data, And that can be in healthcare, that can be like patient data. And you need to do some data selection and filtering. And after that, there's a pre-processing stage that you do the normalization and cleaning and all these stuff. And then you train and test your model, right? So this is the part you run experiments, that it can be multiple types of models and the methods. Like I said, it can be actually combined with rule-based models. And you have all these setups, you want to test everything there, and you finally generate a result. But you actually not, the requirement is actually not deliver the model. The requirement, your result often are actually results for publications and patents and reports. That means, plots, tables, LaTeX code pieces that you can actually put in your final result. And the problem is, like, if we just think about machine learning or this training and testing, people may think about the magic is in the model training and methods, but it's actually not. So a lot of iterations often happen in the first block. That's the data selection and filtering. So how you actually get your problem defined and data selected correctly, that in healthcare actually requires a lot of domain knowledge there, and it requires expertise in medicine and healthcare, and it requires some of the knowledge, you understand the clinical settings. So a lot of times, which means like you actually need to modify and iterate on that first block. And for every iteration, you need to generate all the results fast. So you really want some one button click that you can have the data in and put in some knowledge and get everything done out there. And then in this sense, when I'm talking about this like model training and method, it feels more about some of these auto machine learning setup. It's getting popular out there, but there's actually some subtle differences. So a lot of auto ML systems, existing auto ML systems, are more focused on you put data in, and it's just like train and validate model and give you all the best result of the model. It delivers the best model there and try to help you also deploy the best model. But in the research setting, a lot of times you don't really care about that's only the best model. And you actually need to reason and do a solid test on the model. And you actually need to often, so for example, different models may actually require different imputation techniques. And you may actually add in some like a slightly different rules based on your domain knowledge to actually slightly change that. And your final, as I mentioned, your final result is actually plots, tables, and all these reports and patterns you want to generate. And it's not really about the model itself, right? So, and also in healthcare settings, especially in healthcare settings, a lot of times you cannot really fast iterate on a model. You actually, your experiments is focused on how you can do a lot of experiments and testings and getting everything settled, answer every question you can answer. And then finally you have that one model, then you want to get that model and patent or like approved by FDA, for example. So in this setup, you really want faster experiments. And even you just feel like the model training may not take that long. And also, some of the part is really just generate some plots and tables. And trust me, these number of experiments can add up very quickly. For example, if you need to try 2-3 different kind of cleaning settings, and then also try 5 different models, and then you need to generate plots and tables for different formats for the publications and reports and patents. And because of the regulatory requirements, you may actually need to generate different formats and all these things. These can add up very quickly. Very fast, your pipeline will be, every time you want to change the data selection and the filtering in the first block, and it will take hours to actually run experiments. That's just not really feasible. It really just slows down development. And how can you actually, if we using Ray, it will be easier for the data scientists to be able to run these things in a shorter amount of time, and just a one button click that actually get all the results. And it doesn't involve that much external tools to do this. And I just want to emphasize this again about how I feel like run experiments in a larger scale is actually really beneficial and important for the research and the prototyping. And not only is that you can have the iteration faster, but also, if a lot of times I've seen data scientists actually only developing and testing on a smaller scale, just because the time is really limited. They can only do like small scale testing end to end. But on the other hand, for example, some of the NLP, if you have real emoji characters in it, that may actually errors out and hits your performance and have some issues, but you won't be able to notice this until you actually run your testing on a relatively larger scale. So you can actually hit into all different kind of cases. So being able to actually test on large scale for data scientists is actually very beneficial. And also running things end to end is also very beneficial for data scientists. Like I say, so a lot of times, many problems data scientists cannot be just narrowed on a single point. They do need to be able to extend their scope and have more control to the upper stream and to the downstream, and to get to the end-to-end testing. And also, even some of the tasks feel small and it multiplies and it can add up like super quickly. And being able to iterate fast is often business critical. And I just want to have one more slide and try to mention some extra challenge we have, which this happens both at primary AI that we need to deal with large enterprise customers and government customers, and also for in like healthcare settings that we need to deal with hospitals and some of the healthcare providers. To serve these enterprise customers, it often requires on-prem deployment. That's different from if you just actually sell consumer apps and host and deploy everything by yourself in your own cloud settings. So if you go to on-prem, you will see that there's a very wide range of resource availability. So, and the customer will actually tell you different requirements. So these are actually some of the pieces we actually heard about. So customer will ask, some customer may say like, hey, you can have the largest instance possible, but we really need to do this as soon as we can. But on the other hand, you can go to some other customer and they will tell you, we actually, we don't want to spend that much money right now. And we're okay with just running the pipeline overnight. We're just like, we can run this daily. And we just like do this overnight and we'll check the result every morning. And you can get customers say like, hey, we know that your GPU models are good, but we don't have it, and we cannot get approved for that. And but we'll give you large nodes instead. You can have a really large node net there. So you can have these like a very weird, not weird, but wide range of requirements available out there. So when that happens, so if you, this is the place that you cannot just set everything in a way that has a lot of external dependencies and set up things in a very complicated way. And so you actually want your code and your model and plus your processing code to be as portable as possible. So for Ray, it's actually provides us a good opportunity to have less dependencies externally for scaling. And for some of these pipelines, you can actually you can actually just still remain in your Python ecosystem, but your code will still be able to scale. That actually really narrows the gap between the experiments and the production, and that's also often critical. This is all I have today, and feel free to ping me if you have any extra questions. I'm really happy to talk about this. Like I say, this is more about doing fast iterations and experiments in smaller scale settings, but it can also scale up quickly. Yeah, thank you very much.